Polarity, it's going to be the topic in this lesson. Now, we're in the very last lesson in a chapter on chemical bonding, and earlier in the chapter, we already introduced the idea of electronegativity. So we learned that fluorine was the most electronegative element, and the closer you are to fluorine, the more electronegative an atom is. But in this lesson, we're going to take a little closer look at what electronegativity actually is and how it can lead to a bond being polar, how the different atoms one can be partially positive and one can be partially negative. And we'll show how that can actually lead to the molecule itself also being polar. So we'll talk about bond polarity as well as molecular polarity in the course of this lesson. This lesson is a part of my high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I release a new lesson. Okay, so we're returning to electronegativity here. And again, fluorine is the most electronegative element. And in this section, I've once again posted a copy of the table of electronegativity values, that Pauling scale. And fluorine's got a value of 4.0, highest on the list for sure. And you definitely should remember that, again, fluorine's first, oxygen is second. After that, though, suffice to say, the closer you get to fluorine, the more electronegative the element is going to be. Now, we first want to talk about what electronegativity is and how does it result in bond polarity. And again, this is something we've already addressed to a certain extent, but we're going to compare a carbon-oxygen bond to a carbon-fluorine bond. And what you'll find out is that carbon and oxygen have a significant difference in electronegativity. Carbon's got a value of 2.5 on the Pauling scale and oxygen 3.5. And any difference that's bigger than 0.5 is going to end up being polar. Now, as long as it's less than 1.7, it's a polar covalent bond. And if you recall, anything over 1.7 was actually going to make it ionic. So with a difference of 1.0, it is a polar covalent bond. What electronegativity actually means is that the shared electrons between carbon and oxygen are going to be pulled more tightly closer to the nucleus of the more electronegative atom. So this electronegativity is a description of the atom's ability to pull shared electrons closer to it. And so oxygen being more electronegative than carbon is going to pull these electrons closer to it. And what the result is going to be is oxygen is going to end up with a partial negative charge because the shared electrons are going to be a little closer to him. If they were shared exactly equally, there'd be no distribution of charge here. But being pulled a little bit closer, partial negative. So, and because carbon is not going to have his fair share, he's going to end up being partially positive. Now, if you didn't see my other lesson on this, the Greek letter delta here is a symbol we use to mean partial. You'll see it again in a calculus class for like partial derivatives, but here it means partially positive, partially negative. And the idea is that we're not doing a full transfer of these electrons. They're still being shared, just shared unevenly. So it's not like we're going to have a negative one charge and a positive one charge, which would indicate a full transfer of electrons. It's just that they're shared unevenly. So it's going to be some fraction of a negative charge and some fraction of a positive charge, but definitely not a full +1 or -1 charge. All right. Well, carbon-fluorine bond is also considered polar. Again, carbon value of 2.5, fluorine a value of 4.0. So now the difference is 1.5. This is a even more polar bond. And that's the first part of this lesson, is that the bigger the difference in electronegativity, then the greater the polarity of that bond. And so we can talk about degrees of polarity. And you might be asked to identify which of these two bonds is more polar, and as we just discovered, it is the carbon-fluorine bond. And just, again, you're not going to have to memorize all the values on the Pauling scale. Just based on where they're located on the periodic table, you should have an idea of how electronegative they are. And again, the bigger the difference in electronegativity, the more polar that bond is. And you definitely should have seen that carbon-fluorine bond would be a bigger difference in electronegativity and a more polar bond than that carbon-oxygen bond in this case. Now, we also represent this in one other way. We often draw an arrow from the less electronegative atom to the more electronegative atom with a little plus sign next to the less electronegative one because it is partially positive. So same thing on this. And so these are representing the bond dipole, and you can represent it either one of these ways, either with an arrow to represent the bond dipole or with drawing out the actual partial plus and partial minus. But what we'll see when we talk about molecular polarity, drawing these individual bond dipoles with the arrows is super handy, as we'll see just a little bit. And we want to do this with one other bond here. So if we want to compare the carbon-fluorine bond to the carbon-chlorine bond. And once again, we should be able to figure out which bond is more polar. And so again, carbon's down here at 2.5, fluorine's up here at 4.0, chlorine, it turns out, is at 3.0. But even without those values, you should be able to look at this and be like, oh, there's a bigger difference in electronegativity between carbon and fluorine than between carbon and chlorine. And you might kind of look at it like this. You might say, okay, well, here's carbon. Fluorine's the highest, and fluorine and chlorine is a little bit lower. And so we're going to see a smaller difference in electronegativity between carbon and chlorine than between carbon and fluorine. And so once again, the carbon-fluorine bond in this case would also have a greater dipole moment and be more polar than the carbon-chlorine bond. So this is a kind of common question you might get on the exam. You might have to just identify which is the most polar bond, and they're just looking for the biggest difference in electronegativity. All right, so how do we apply this to molecular polarity? So in this section, now we have to take into account what we learned about molecular geometry and what we've now learned about bond polarity, and see if it leads to a molecule overall being polar. So let's draw a few molecules out and see how this works. All right, so first thing we're gonna do is compare these two, and what we wanna look at is do we have any polar bonds first? Because if you have a molecule and there are no polar bonds in it, then it's a non-polar molecule. So however, if the molecule has polar bonds, it has a chance to either be polar or non-polar, depending on how polar each of those bonds are and how they're related to each other in space three-dimensionally based on the molecular geometry. So if we look at both carbon dioxide here and COS here, they're both linear in shape. And that's the first thing we should realize. Two electron domains, it's going to be linear. Okay, that means that these are oriented, these two carbon-oxygen bonds, or the carbon-oxygen and the carbon-sulfur bonds, are oriented 180 degrees apart. Now, Mr. Lewis makes them look 180 degrees, but that's not enough. Mr. Lewis makes everything either look 90 or 180. That doesn't necessarily mean they're going to be 90 or 180, but in this case, they really are 180 degrees apart. We know that based on the molecular geometries being linear. Now, if we look at the bonds here, the carbon-oxygen bond, that is definitely a polar bond. Oxygen's more electronegative than carbon, and so we can draw an individual bond dipole pointing off to the left from less electronegative atom to more electronegative atom. But the other carbon-oxygen bond is also polar, and so we can draw another bond dipole off to the right. Now, with these two being identical bonds, it turns out that these bond dipoles are equal in strength. But they point exactly 180 degrees apart, and so it turns out they're going to cancel. If we added these as vectors, which you might not know what those are, you'll learn about them more in a physics class. But because that's a little bit of a nebulous term possibly for you at this point, so think about pulling on this carbon equally to the left and equally to the right. Would this carbon go anywhere? Well, no, it wouldn't. Okay, and as a result, that's a way of kind of predicting that these bond dipoles are going to cancel. What's really going on here, so if you look, the oxygen should be considered partially negative and the carbon partially positive. When we say that a molecule is polar, what we really mean is that there are two poles. We mean that we say that it formally has a dipole moment. And a dipole moment means it has two poles, a positive pole and a negative pole. And so again, we use that analogy that the Earth has a magnetic dipole and it has a north pole and a south pole. Well, this is an electric dipole and it has a positive pole and a negative pole. And so if we look at this molecule, though, and we say, which side of the molecule is more positive? Well, the positiveness is all in the center of the molecule. And then if we say, which side of the molecule is more negative? And we say, well, it's spread out in two places. Well, where's the average location of the negative charge? Well, the average of this position would be once again in the center of the molecule. And so in this case, the positive pole is the center of the molecule. And the negative pole averaged out is also in the center of the molecule. And so there's actually not two different poles. The positive pole and the negative pole are both in the center of the molecule. So that's what we really mean by this is doesn't actually have a dipole then. There's not two separate poles. When both poles are averaged to the very center of the molecule, no dipole moment, and we'd say this molecule is non-polar. Now, if we look at his neighbor right next door here, so we've still got a polar carbon-oxygen bond, and then we've got a carbon-sulfur bond, which we'd probably also predict to be polar, but it's a much smaller difference in electronegativity, and I'm going to represent that by drawing a much smaller bond dipole arrow. And so as a result, these two bond dipoles do point 180 degrees apart, but they're not equal in magnitude. The one on the left is bigger than the one on the right. And so if we add them as vectors, or if we say I'm pulling left with this one, I'm pulling right with this one, well, the one pointing left is going to win. And as a result, we'll say that this molecule is polar. And if they wanted us to draw the overall dipole moment of the molecule, what you do is you add these two and figure out that the overall one points to the left because the one pointing to the left beats the one pointing to the right. It overcomes it, if you will. And so you can draw individual bond dipoles, but for polar molecules, you can also draw the overall, forgot that part, molecular dipole as well. Notice the nonpolar molecule, there's no molecular dipole moment you can draw. So there's no like overarching arrow for the entire molecule because the individual bond dipoles actually cancel. All right, so the next three examples we're going to take a look at across the top here. So one thing to note, I'm going to leave lone pairs off the outer atoms for clarity's sake. So no lone pairs drawn in on these chlorines. However, if the central atom had any lone pairs, I would draw those in. Boron's an octet rule violator, no lone pair. And in this case, the carbon's got filled octets, no lone pairs on those. But I'm leaving them off the chlorines and the fluorines on these atoms just for clarity's sake. So we want to evaluate these three molecules and figure out if they're polar or not. And again, one of the things we'll typically do is draw in these lovely individual bond dipoles and then say, do they all cancel, yes or no? So, and in this case, it looks like the top two cancel and then nobody canceled this one. So we're like, he's polar, look, he's polar. So however, we got to be careful because once again, Mr. Lewis makes everything look like it's either 90 degrees apart or 180 degrees apart. But if you look, you now understand molecular geometries. And with 1, 2, 3 electron domains, you should predict that this lovely boron atom has a geometry around it that is trigonal planar. So Mr. Lewis says, these look 180 and these look 90. But he's wrong, right? All of the angles are 120. If we actually tried to redraw this with proper angles, we might draw it like this. So with 120 degree angles all the way around, and now all of a sudden, with that trigonal planar geometry, these three actually will cancel. If you tried to pull on this boron equally in three directions, all 120 degrees apart to the corners of like an equilateral triangle, that boron's not going to go anywhere. All three of these net are going to cancel. Now, one thing you should note, when you have a molecular geometry that's linear, or a molecular geometry that's trigonal planar, or a molecular geometry that's tetrahedral, in each of these cases, the central atom doesn't have any lone pairs. And if you've got one of those molecular geometries with all identical atoms around the central atom, those individual bond dipoles will cancel, and it will end up being nonpolar. So, which makes the next one easy. So in this case, all of these carbon-fluorine bonds are polar. So, and you might be inclined to look at this and be again, oh, these two point 180 apart and these two point 180 apart and everything canceled, life is good. Well, it turns out everything does cancel, but not because they're all 180 degrees apart. So in this case, you got to remember that 4 electron domains means this is actually a tetrahedral geometry. If we tried to draw this and represent it three-dimensionally, sometimes we do something along these lines. And to represent three-dimensional objects on a two-dimensional piece of paper, we use wedged bonds to show things that are coming out of the board, and then we use these dashed bonds to show things that are actually going back into the board, and then these two bonds are in the plane, and this is one way to represent that tetrahedral shape. And so in this case, if we draw in these individual bond dipoles, they will indeed cancel, but not in the way that maybe we thought they might by looking at the Lewis structure. But they do indeed cancel. And again, the key is, as long as you have all identical atoms around either a linear shape, like we had with carbon dioxide, or around the trigonal planar shape, like we do with BCl3 here, or like we have with the tetrahedral shape with CF4 here, they will indeed, all those bond dipoles will cancel, and your molecule will overall be nonpolar. Okay. Now, if you've got lone pairs on the central atom, it turns out that those are going to throw off some of the symmetry. And for all the examples we're learning for up to 4 electron domains, they're going to actually end up being polar, as we'll see here in a little bit. So if you end up learning about expanded octets with either 5 or 6 electron domains, you will learn there's a couple examples where the central atom has lone pairs that still end up nonpolar. But for what you're learning in just up to 4 electron domains, lone pairs on the central atom are always going to result in the structure being polar. All right, let's look at CH2F2 right here. And if we look at this one and the CH bonds, you might recall that CH bonds are considered nonpolar. And so there's not much of a dipole moment associated with them, so no arrow to really draw in. But the carbon-fluorine bonds are polar. And if you look, then they look like they point 180 degrees apart and they should cancel. Except we got to remember again that Mr. Lewis is a liar. He makes everything look either 90 or 180. But this is a tetrahedral geometry. It doesn't matter which two of the bonds you choose. All of these bonds, whether I choose these two or these two or these two or these two, they're all 109.5 degrees apart. So if we redraw this to kind of give a better representation of what's going on here, and use our handy dandy three-dimensionality, so we'll see that they definitely only point 109.5 degrees apart. And so those individual bond dipoles for those carbon-fluorine bonds are not going to perfectly cancel. And as a result, this molecule is going to be polar. And if it's going to be polar, then we should be able to draw an overall bond dipole just like we did here. Again, the one pointing left beat the one pointing right, so the overall pointed left. Well, in this case, they're not pointing exactly opposite, and so you have to figure that they are going to cancel each other to some degree and be additive in some degree, and you kind of take the average of them, and so the overall molecular dipole would be going right down the middle between them. And sometimes you're asked to provide that or choose the one that has it properly drawn in on a multiple choice test. Cool, let's take a look at just a couple more. All right, last two, we looked at these in terms of molecular geometry and we figured out that NH3 is trigonal pyramidal and that water over here, H2O, is bent structure. If we look, the nitrogen-hydrogen bonds are definitely polar. So in this case, hydrogen's more electronegative than nitrogen's more electronegative than hydrogen. Let's get that right. So same thing over here. Oxygen's more electronegative than hydrogen. And if you take a look at this, we said just a minute ago that if the central atom's got lone pairs and you have polar bonds, then it's going to be polar. But that doesn't quite look like that's the case over here with water. But once again, you got to remember what you know about molecular geometry here. This is a bent structure. These are not 180 degrees apart. Otherwise, it'd be called a linear structure. This is bent, and a proper three-dimensional representation of water would reflect that bent structure. Again, and this is another case where Mr. Lewis is a liar. It's not 180 degrees. And if we take a look at these individual bond dipoles now, we can see that, yep, they're not going to cancel perfectly, and this molecule is definitely polar. And if we take the average of those two individual bond dipoles, we can see that there'd be an overall molecular dipole right up the center of that molecule. Now, if we look at ammonia here, here they don't look like they cancel anyways, but again, we should really take into account the real three-dimensional geometry here, and I'll draw that once again over here. And if we draw those individual bond dipoles in one more time, so they're definitely not going to all cancel. And the way we've drawn this, they all point up in one way, shape, or form. And going right up the center of this molecule would be the overall molecular dipole. It's kind of like these three hydrogens are the three legs of a tripod, and right in between the tripod, straight vertically up, would be the molecular dipole. And once again, that makes this polar. So to sum it up, if you've got, you got to have polar bonds to be a polar molecule. That's the first part. So if there are no polar bonds in the structure, it's going to be a nonpolar molecule. But if you have polar bonds, they can cancel, they cannot cancel. If all those polar bonds, if their dipoles cancel, it's nonpolar. If they don't cancel, it's polar. So, and if it is a linear, trigonal planar, or tetrahedral geometry with all identical atoms all the way around, that's when they cancel and it's going to be nonpolar. If there are any lone pairs on the central atom, or if you've got different atoms coming off the central atom, not just all fluorines like was the case here, but two fluorines, two hydrogens, or here where it's one oxygen, one sulfur, then they're not going to cancel in that case either because there's a difference in magnitudes, and it'll end up being polar in that case as well. But if you've got identical atoms around it, and it's either linear, trigonal planar, or tetrahedral, that's when they cancel as well. Cool. This is what you need to know about both bond polarity and molecular polarity. And we'll find out that this plays a big role in some of the properties that molecules have. And we'll find out it can affect things like melting point or boiling point. And polar molecules actually tend to have higher melting points and boiling points than non-polar molecules of similar size and things of this sort. So we'll find out this idea of being able to figure out if a molecule is polar or not is a big deal. And in a couple chapters, it'll be a useful tool when we start actually comparing melting points and boiling points of different solids and liquids. If you have found this lesson helpful, would you consider giving me a like and a share? A couple of the most helpful things you can do to help promote the channel. If you are looking for the study guide that goes with this lesson, or if you are looking for practice problems, check out my premium course on chadsprep.com.